Okay, let's start with number 7 because that's the one I hadn't saved right last time. And so when I printed it out, it didn't print right. And then it didn't have part A, B, and C written down. It just had the top part. But now it has the different parts written down. So 7, I'll let you read it because you have the paper. So I'll let you read it for a second on problem 7 on the test review. And it tells what M means math major, C means computer science, E means engineering. All right, so first, and then look at the first part. It says there is an engineering student who is a math major, right? So how do you write the sentence, there is an engineering student who is a math major? So exists a student, X, right? And then what do I say about X? There exists a student, X, such that what? So what does it mean if somebody is an engineering student who is a math major? How many majors do they have? 2, so that means that there exists X, and then how do you say somebody is an engineering student? What predicate do you use? E, right? And then you say they're also a math major as well, right? So basically there exists X such that E of X and M of X. And then you can close the parentheses like that. Perfect. Okay. Then it says every computer science student is an engineering student. How do I say that using quantifiers, variables, and predicates? Every computer science student is an engineering student. How do I say that? So every means what? What symbol do you use to represent for every? You use the for all symbol. It's like an upside down capital A, right? So for every student, how do you say that if they're a computer science student, that they're also an engineering student? How do I say that? Every computer science student is an engineering student implies that if you're a computer science student, that you're also an engineering student, right? So that means that if how do you write the phrase if something then something? What symbol represents if something then something? I'll give you 3 options: the stop sign, a turn sign, or an arrow. Arrow, right? So how do you write if you're a computer science student, then you're an engineering student? That's written as C of X, arrow, E of X, right? So for all students, if they're a computer science student, they're an engineering student. That's how you write it. Then it says, this next one says, no computer science student or engineering student. How do you say that? No. Now, by the way, the no actually really represents for all as well. So how do you say no computer science student is an engineering student? That means that all computer science students, for all computer science students, none of them is in engineering. So that means for all students, if they're a computer science student, that implies that they're not an engineering student, right? And then read the next part. So read it out loud to yourself, then let's do it. It says some computer science students are also math majors, right? So the word some means there exists at least one. The word some is very vague in logic. It really just means at least one because there's no quantity associated with some except for at least one. So some could be 5 or 6, but it really just means at least one. That could still be some. Like, for example, if you knew one friend who hated your coach, you could say, some people I know hate my coach. And that'd be true, right? Because it doesn't have to be 2 or 3 as long as there's at least one. So how do you say some computer science students are also math majors? It's not going to be all. It'll just be there exists at least one, which is that symbol. But exists at least one student. What do I say about that student? They are a computer science student, right? And a math student. Yep. So it's kind of like part A. but it's just talking about there's at least one who's a computer science student and a math student, but not that. So anyway, and then what about the last one? Some computer students are engineering students and some are not. How do I say that? It's talking about two students, so you have to use two existential quantifiers. So there exists X and there exists Y such that what? So if there's some computer science students or engineering students and some are not, that means that there's at least one computer science student who is an engineering student and so there's at least one computer science student who is also an engineering student as well, right? And the other one is a computer science student, but not an engineering student, right? So there's at least one student called X who exists and at least one student called Y who exists, such that there's four things that are true. Student X is computer and engineering and student Y is computer but not engineering. So there you go. Any questions about that?
Want us to use another set of parentheses.
Well, so the thing is, if you have four and signs all in a row, there's really no ambiguity as to where you put the parentheses because they all have to be true. So no matter where you put the parentheses, they still would all have to be true for that to be true.
Okay.
So you could put parentheses like this and say that that's true and that's true because they're separate students. But logically, there's no need for parentheses, and it talks about that a little bit in the book. In certain things, as if you have the same symbol repeated a bunch of times, you don't really need parentheses around them because the associativity property wouldn't really matter because they still all ultimately have to come out to be true in order for it to be true. Okay. So let's talk about we already did number 8. Now let's do number 9. So have you ever wondered about this yourselves before? That if you take two odd numbers and add them together, you always get an even number? Have you ever noticed that before? Like if you pick the number 3 and the number 5, what do you get? You get another odd or another even? Get an even, right? So is it possible to prove that? What about if you subtract them? What's 3 minus 5? And that's also an even. So how do I prove that the difference of any two odd integers is even? So first of all, let's define some things. Even numbers. What does an even number X actually mean? How do you define what an even number X is? And an even number X is called even if it's a multiple of 2. So that means there exists a constant such that X is equal to a multiple of that number, right? So an even number means there exists some integer. I'm going to call that integer C, such that X is 2 times that integer C. And then, by the way, the universe of discourse, I'm going to write this at the top because this is actually, math is actually not perfect, but the universe, sometimes they're a little bit ambiguous, but the universe of discourse is going to be integers. So that means that when you say there exists C, it's not like a fraction, it's an integer. In fact, a better way of saying that would be, who remembers the symbol for integers from the book? Remember that little table that we looked at the bottom of the left side of one of the pages in the book one time? If you read the book. And then remember when I talked about how that their definition of natural numbers was wrong? And that no math major should ever learn that definition? But anyway, okay, so the letter for integers is called Z. Z just means 0 or plus or minus 1 or plus or minus 2. It means any positive or negative integers like that. And then it keeps on going forever, ... So what we could say to make this a more proper definition of even numbers is there exists a constant that's in the set of natural numbers Z such that X is 2 times that integer C. But anyway, that's just a little bit overkill though. So basically just remember an even number means that it equals 2 times some integer. How do you define an odd number? How do you define an odd number? Why? Then you said that there exists a constant that's some integer such that that value y is equal to some 2 times that constant plus 1. You could also say minus 1. They're both equivalent. So an odd number is always a multiple of 2 plus 1, because if you take an even number and you add 1 to it, it makes it odd. Or you could say 2c minus 1. Now that also makes it odd. So in order to prove the difference of any two odd integers is even, we need to take two odd integers, odd minus odd, and prove that it equals an even. So that's our goal. How do we prove that when you take the difference of two odd numbers, you get an even? So let me write a quick proof for you and you make sure you memorize this, or if you want to, you can try to think of a way to rephrase it, but probably it's better to just memorize it. So you always start with the word let when you're proving something like this. So let A and B be two odd, hold on, my screen's not working very well. Integers. I have to be gentle, I think, when I'm doing it. Let A and B be two odd integers. So we're going to assume, because of that property of what the definition of what an odd integer is, assume that A equals 2. Instead of saying C, I'm gonna say J. 2J plus 1 and B equals 2K plus 1, because, and then you're gonna say like J and K are integers. And that says Z. To assume A equals 2J plus 1, B equals 2K plus 1. And now you might say, well, why are you allowed to assume something if you have to prove it? Well, because remember, any odd integer, the definition of odd integer means that you always can assume that it equals 2J plus 1 and equals 2K plus 1. You can't assume that both of them equal 2J plus 1, though. Why can't you assume that both of them equal 2J plus 1? Why can't you just assume they both equal 2J plus 1? Why can you assume that one of them equals 2J plus 1, but the other one has to equal 2K plus 1? Anybody understand why you can't do both equal to the same thing? Because although you can assume that any odd integer is in the form of 2 something plus 1, you can't assume that both integers are equal to the same value of 2 something plus 1. Because we don't know if A and B are equal to each other, right? So that's why we have to use 2J plus 1 and for one of them and 2K plus 1 for the other one. Now let's subtract them. So then A minus B is equal to 2J plus 1 minus 2K plus 1, right? Which is equal to 2J plus 1 minus 2K minus 1, which is equal to, what is 1 minus 1? 0. So it's equal to 2J plus minus 2K, which is 2 times J minus K, which is equal to an even number, right? So therefore, A minus B is even. Proof complete. And you can draw a little box when the proof is complete. So that looks like A times B, my fault. Let me make it longer. So therefore, A minus B is even. So when you say, so any two odd integers, that's the only thing that we have, that's called the antecedent of the proof or whatever. So like this is what you're starting with. We're starting with any two odd integers. And with any two odd integers, you can always assume that they're equal to the form 2 times something plus 1. So we assume that, which is legal. And then we subtracted them. When you subtracted them, you got something that was in the form of 2 times something, 2 times the difference of them. Anything that's in the form of 2 times an integer is an even number by definition. So therefore, since A minus B equals 2 times something, it's an even number. So that's the proof of that. Okay, let's go ahead to number 10. Perfect. So 10 3.5959, and it just keeps repeating forever. So basically that, you can draw a bar over it as well, is what that means. Express that as the ratio of two integers. So let's do it. First of all, count how many digits are repeating. Actually, first of all, where does the repeating pattern start? Does it start right after the decimal point or later? It starts right after the decimal point, right? So the first thing you do in these kinds of problems to express a repeating decimal as a fraction, because remember, any repeating decimal is actually a rational number, which means it can be expressed as a fraction. So how do you express a repeating decimal from the infinite form to just a regular fractional form? The way you do it is you multiply by a multiple of 10 such that the repeating decimal, it begins right after the decimal point. So, which it already does, right? So it already begins right after the decimal point. It already begins right after the decimal. Right after, sorry, I started writing cursive by mistake. Right after the decimal point. So now we're going to multiply by a number by a power of 10, or a multiple of 10 or whatever, by 10 to the some power, such that we get one copy of the repeating decimals before the decimal point. So one copy of repeating decimals, of repeating digits, is before the decimal point. And you have to make sure it's just one, not more than one, not 1.5, just exactly one. So how many digits are there repeating? 2 or 3? 2. So we're going to multiply by 10 to the power of 2. So we're going to take 100 times 3.59 repeating, which equals 359.59. And it's because 59 always repeats, it still just has more 59s after the decimal anyway, right? So we multiply by 100 because there's 2 digits repeating. What if there were 3 digits repeating? What would we multiply by if there were 3 digits repeating? 1,000, right? Because you need to multiply by 1,000 in order to move 3 digits over before the decimal point. Now subtract the bigger one minus the smaller one. So you do bigger minus smaller. So you do 359.59 repeating minus 3.59 repeating equals, what does it equal? 3. So remember, where there's 2 subtractions actually happening before the decimal and after the decimal. So 359 minus 3 is 356, you said, right? Sorry, when I write on the screen, my numbers loop over too much sometimes. And the 0.59 repeating minus 0.59 repeating just cancels out. So that's that step. Now, how do we get the other part of the fraction? That's going to be like the top of the fraction. How do we get the bottom of the fraction? Well, remember this, I'm trying to represent 3.5959. I'm trying to calculate what that is as a fraction. So that's like x. I'm solving for x. So what I know is I did 100x. That represents 100x. And this represents x, right? So I know the 100x minus x. So does that make sense to you, first of all? Do you understand that this represents 100x? That multiplied by 100. That represents x, right? So now 100x minus x is 99x, right? So then divide by 99. So x equals 356 over 99. Then that's the solution. Unless it can reduce. I don't think it can reduce, but that's the important part of the problem, though. So to represent the repeating decimal as a fraction, first multiply. So by the way, what if the 0.59 had not started right after the decimal point? What if the 0.59 at the top had started like 1 unit after the decimal point? What would you have to do then? Like, what if the problem had been 3.1595959? What would you do in that case? So I'm saying, like, what if this problem had been 3.159595959? What would you have to do first before you even started? You'd have to multiply it by 10 to get that 1 to move forwards, right? So in that case, you would have done 10 times 3.51555 or whatever would have equaled 31.595959. And then what would you do down this part? Well, then you take the 100, you take the 359 1.59 minus the 31.59 equals that. And then you'd have 100x minus 10x equals this. So then you'd have 90x equals the number instead. So that's the basic pattern. As you multiply by a power of 10 big enough so that the pattern starts right after the decimal point, and then you get that number. And then you multiply by a power of 10 so that one copy of the repeating digits actually moves before the decimal point, and then you get that number. And you subtract them, and the decimal points will cancel out. Then you replace the original numbers you subtracted with how many x's they were, like 100x minus x. Subtract those, and then you divide, and then you get the x represented as a fraction. Okay, perfect. Sorry I'm taking so long. I could have gone a lot faster on this. So number 11, it says how many zeros are at the end of 75 to the power of 6 times 24 to the power of 5? So first of all, this is going to be, you're going to have to use a little bit of strategy at first. How do you figure out how many zeros are at the end of a number? The only way you can get a 0 at the end of a number is if and only if what? So how many zeros are at the end of that number? So we don't even know what 75 to the power of 6 times 25 to the power of 5 actually is. But we still want to know how many zeros are at the end of it though, right? But you can only have a 0 at the end of a number if it's a multiple of 10, right? So we have to figure out how many 10s are inside of it. But factor out 10, what are the factors of 10? 5 and 2. Correct. And 5 and 2, right? I made a mistake. Sorry, my fault. Did anybody catch my mistake? I wrote 25 to the power of 5 instead of 24. By the way, if it would have been 25 to the power of 5, how many zeros would have actually been at the end of it? 0. Because guess what? Well, I'm just about to explain. So the only way you can get a 0 at the end is if there's a multiple of 10 somewhere in the number, right? And the only way that there can be a multiple of 10 is if there's a factor of 2 and a factor of 5. So let's factor these out. What are the factors of 75? It's 25 times 3, which means it's 5 to the second times 3 to the first, right? And then what are the factors of 24? Broken down as far as possible. 24 is 6 and 4, or 3 times 8, right? It's 3 times 8. So an 8 is 2 to the third. So it's 2 to the third, which is 8, times 3 to the first. And that's all to the power of 5. Now let's multiply those powers 3. So what's 5 to the second to the times 6? That's 5 to the what? 12. Because 2 times 6 is 12. What's 1 times 6? 6. And what's 3 times 5? And then what's 1 times 5? So by the way, the 3s don't really matter. Only the 5s and 2 matter. So how many 10s would you be able to get out of this? If you have 12 5s total, but you have 15 2s, how many 10s can you get by multiplying 12 5s and 15 2s together? Remember, the only way you can get a 10 is if you have both a 5 and a 2 to multiply together. So you'll have 12 5s. Each of those 12 5s can be multiplied by 12 2s. So you get at least 12 10s. But can you get more than 12 10s? No, because those three extra 2s that are in that number 2 to the 15. See, there's 15 powers of 2, but only 12 powers of 5. There's 3 more powers of 2 than there are powers of 5. So there's just 3 extra 2s that do not make 10. They just leave you with an extra 8, but not a 10 though. So there's actually 12 10s in that product. So there's 12 total 10s. So that means that there's going to be 12 zeros at the end of the number. So it's really just asking you to factor out the prime numbers. That's really all it's asking you to do. And then just use logic to figure out how many 10s there would be. Okay, let's go ahead and do 12. Okay, so we know this. We know that if b mod 12 is equal to 5, what is 4b mod 12? So in other words, if division of b by 12 gives a remainder of 5, what is the remainder when 4b is divided by 12? By the way, that's just you don't need to pay attention to that as long as you've been listening to what we've been talking about with like the last couple of weeks about encryption and things. So what's one of the things we learned about with encryption? Or that we learned about modular equations. Modular equations. What did we learn? So b mod 12 equals 5 means what? How do I write that as a modular equation? That means that b is congruent to 5 mod 12. Remember? That's how you write it. And what property do you know about modulo or modular equations? What property do they have? You can still multiply them on both sides by an integer, right? So if I want to know what 4b is congruent to mod 12, I can just multiply both sides by 4. So multiply 4b would be congruent to, what's 4 times 5? 20 mod 12. Exactly. So that's the second step. And now what's the third thing you know about modular equations? In fact, the whole purpose of modular equations actually is when you put in the equation in this form, you can always reduce both sides by what its modular base is. So, and that means you replace any number or any factor of a number with its remainder after dividing by 12. So what's 20 mod 12?
8.
8, correct. So 4b is congruent to 8 mod 12. So therefore, the answer to the question, what is 4b mod 12? The answer would be 8. Perfect. Okay, now do we have only a little bit more? So let's do a trace table for the loop. So by the way, this is one thing that I really expect you to be able to do. It shows that you are able to logically think through computer programming. So ready, let's do number 13. Okay, so E is equal to 2. And by the way, you don't have to use the colons. That's just what the book uses. E equals 2, F equals 0. What I want you to do when you're doing a trace table is to just write every assignment the computer would actually do as it runs the code. So every single assignment the computer does as it runs the code, you just need to write that down. So the next assignment the computer would be doing would be to do k equals 1. And then after it does k equals 1, it goes inside the loop. And it would do E is equal to E times K, which would be equal to, and then you plug in the current values of E and K, which is 2 times 1, which is 2. So E equals 2. Now, by the way, you don't have to write this step right here. You don't have to write that step right there if you don't want to, in fact. But I think you do need to write that step right there for me to give you full credit, though. Because I want to know that you really plugged in, that you knew what you're doing when you plugged in the numbers. So the next step is F equals E plus F. Well, E is currently 2 because E just got defined in one line before, right? So remember, when you're doing this code, you look at the current value of E. So don't go back up to the top and look at that value of E, even if it's the same, you should still ignore it. Only look at the value of E that's right before. So, because computer programming code is a dynamical system where everything is constantly being updated and changed all the time. You should only look at the most recent value of it. So 2 plus 0. So f would be 2 plus 0, that's equal to 2. Now you're going to go back to the top of the loop because the loop runs from k equals 1 to 3. So the next value is k equals 2. And then you're going to go inside the loop again, and e is going to equal e times k, which is now equal to 2 times 2, which is now equal to 4. And f is going to equal e plus f, which is currently 4 plus 2, which is equal to, oh, by the way, I skipped a step. I didn't really skip a step. It's okay with me if we're at 4 plus 2, but I'm going to try to show one extra step though. What f is actually defined as, which is e plus f. F is equal to e plus f, which actually is equal to 4 plus 2, which is equal to 6, right? Let me know if you see any mistakes I'm making, because you have to really concentrate hard when you're doing this. Even just looking up and back and forth makes your mind lose track of it. So f equals e plus f, k, and then we're going to go back to the top of the loop again. K equals 3. That's the third part of the loop. Then you're going to do e equals e times k, which is equal to 4 times 3, which is 12. And then you're going to do f is equal to e plus f, which is equal to 12 plus 6 is 18. There we go, perfect. So you're done with that. Okay, now where's my other page of this test? Okay, there we go. Perfect. All right, so then page 5, there's 2 questions left. Any questions about these? So we're done with the trace table. No. Page 5, question 14. It says BK equals 9, BK minus 1 minus 14, BK minus 2. This is actually just a college algebra problem, but it's disguised as a discrete math problem. How do we change it from, what does this say? It says solve the recurrence relation. The way to solve a recurrence relation that's in this form, this is called a homogeneous linear recurrence relation, is by replacing the value of BK. Well, actually, you start with the lowest index. What's the lowest index? BK minus 2. Start with the lowest index, replace that with 1. So now, some of you looked this up online and you found a couple of other ways of doing it, but you replace that with 1. And then you start with the next lowest index of B and you replace that with R. And then you take the next lowest one, replace that with R squared. Now, if you had anything else, like if you had more terms of B, like BK plus 1 and BK plus 2, you'd replace the highest one. You'd replace the next higher one with R to the third, and the next higher one with R to the fourth, and you just keep on going until you got done with them all. We only have 3 though, so we just have 1, we have R, and we have R squared. So then you set this to 0, because this is where you get a quadratic equation. So R squared and minus 9R plus 14 equals 0. Then we factor. So we get R, bring that minus sign down, multiply the minus and the plus to get a minus, multiply the 1 in front of that times the 14 to get 14. Factor the 14 into 2 and 7, and put the bigger one first. So -7 and -2 adds up to -9. And then we get 0. We solve that, and the answers are the opposite numbers as what's inside the parentheses. So R equals 7 and R equals 2, which means, now here's where you have to remember a little bit more theory. So right now we're just doing algebra. But we started with a little bit of theory though, about replacing the BKs with the values of R and with 1. Now we're going back to theory again a little bit. The theory says that once you find the values of R, that the solution to BK is that BK is equal to a constant A. Let me use a small a actually, sorry. No, wait, I can't use a small a, B. Because I already used B, but I'm going to use is it okay if I use C and D? It doesn't matter what the constants' names are. I just don't want to use the same names that we're using for the other variables. So that this just means it's a constant times the first value of R to the power of K. It's usually to the power of N, but they're using K in this problem. Plus another constant times the second value of R, like that. So that means the solution to the problem, BK, and so instead of saying BK equals blank, 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 some strange formula, now we know that the BK is actually equal to the power of 7 plus a power of 2 times any constant, like that. Now, the last and final step we have to do is to determine those constants. That's also just algebra. So the constants that they're given to us is B0. Let me write these at the top. B0 is 2 and B1 equals 1. And now knowing that it's a power of 7 plus a power of 2, we have to calculate the constants C and D. So we're going to plug in B0 for K. So plug in 0 for K, you get B0 equals C times 7 to the 0 plus D times 2 to the 0. Now you plug in 1 for K, so you get B1 equals C times 7 to the 1 plus D times 2 to the 1. Then you simplify. So when you simplify, this represents a system of equations. So you're going to have a system of equations with these numbers plugged in. B0 is 2, so put 2 with the first equation. And then 7 to the 0th is 1, so you just have C. 2 to the 0th is 1, so you just have D. So 2 equals C plus D. Then you plug into the second equation. B1 is defined to equal 1. So B1 equals 1. So 1 equals, and what is 7 to the 1? That's just 7. So 1 equals 7C plus, and 2 to the 1 is 2, so it's 2D, like that. So we got 2 equals C plus D, and 1 equals 7C plus 2D. We have to solve this equation. So multiply, so do you see which is the smallest combination? C is 7C, is the big one. D and 2D, that's pretty small. So we're going to solve the smallest one first. How do we get rid of the 2D and the D? Well, we multiply the D times -2. That's all we have to do. So take this top equation in the system of equations, multiply it times -2. Then you're going to get a new equation, which is -4 equals -2C -2D. And you're going to add that on to the bottom equation. So I'm writing the bottom equation down again. Add these up. So -4 equals -2C minus 2D. 1 equals 7C plus 2D. When you add them up, what do you get? You get -3 equals 5C, right? Then divide by 5. -3 divided by 5 equals C. So that's the value of C. Now we have to find the value of D. The easiest way to find the value of D is to substitute the C into the equation 2 equals C plus D. So we're going to go to the equation 2 equals C plus D. Plug in -3/5 for C. So you get 2 equals -3/5 plus D. And I'm sorry that fraction, they came out to be fractions. I got this problem from the book. But, okay, so -3, or maybe from the online, well, there's not an online homework system that we have, but I got it from somewhere from the book though. So -3/5 plus D is, I'm going to try to give you on the test that has a whole number, hopefully. So it's not a fraction, but how do you calculate the value of D from that equation? We just move the -3/5 to the left side. What is 2 plus 3/5? So it'd be 2 plus 3/5. How do you calculate that? Well, there's a trick in algebra. I'm not sure if you know it. To add a whole number and a fraction, you just start from the bottom, multiply the bottom of the fraction times the whole number, which is 10, and add the top of the fraction, which is 13. Put it back over the bottom, which is 5. So the answer is 13/5. So D equals 13/5. So one final step, which is to write it all together. So where is my formula? Right here. That's going to be the answer right here that I circled in green once I plug in those two constants into that formula. So the final answer is gonna be BK. BK equals C, which is -3/5 times 7 to the power of K plus D, which is 13/5 times 2 to the power of K. So the solution to that problem is -3/5 times 7 to the power of K plus 13/5 from 2 to the power of K. That. Perfect. Okay, then let's go ahead and go to the last and final question. It'll only take a moment. 15. Says prove the following statement by mathematical induction. So when you use mathematical induction, you have to start with statement P1. What is statement P1? P1 is going to be to say that 7 to the power of 1 minus 1 is divisible by 6. Is divisible by 6. So to prove something is divisible by 6, you have to prove it's a multiple of 6. So what is 7 to the 1 minus 1? It's equal to 6. Is 6 a multiple of 6? Yes. So that is a multiple of 6, clearly, because it is 6. So that's a yes. And then you have to assume, when you prove something by induction, you have to assume that statement PK is true. So we have to assume that the statement 7 to the power of K minus 1 is divisible by 6. So when something is divisible by 6, that means that you assume that there exists a number. I'm just going to say the number n. There exists a number n that's an integer, such that the number that you're talking about is a multiple of 6. So basically, the statement PK is that 7 to the K minus 1 is divisible by 6. What it means to say that it's divisible by 6 is just to simply say that 7K minus 1 equals a multiple of 6. So that's the inductive hypothesis. We're just assuming that it's a multiple of 6. Now we have to prove that to prove by induction, you have to prove statement PK plus 1. What is the statement PK plus 1? The statement PK plus 1 is 7 to the power of K plus 1 minus 1 is a multiple of 6. But the thing is, I don't know if it's a multiple of 6, and I can't assume it's a multiple of 6 like I did before. So I'm just stuck. Except I'm not really stuck though, because here's what you have to do. Factor out factor out a 7 from the 7 to the K plus 1. So you have 7 times 7 to the K minus 1, right? So does that step make sense? Take out 1 7 from the 7 to the K plus 1. Because 7 to the K plus 1 literally just means 7 times 7 to the K. Now what I'm going to do is a little trick like this. If you have 7 of something, that means you have, like if I have 7 apples, that means I have 6 apples plus 1 apple, right? So if I have 7 7 to the K's, that means I really have 6 7 to the K's plus 1 more 7 to the K's. Do you agree with that? If I have 7 7 to the K's, that really means I have 6 7 to the K's plus 1 more. Except look at the last part of that sentence though. If I have 1 7 to the K, that's just the same as 7 to the K. And remember, I already know from the previous assumption that 7 to the K minus 1 is a multiple of 6. So therefore, I know that 7 to the K minus 1 is equal to 6n. So this statement right here is equal to 6 times 7 to the K plus 6n. Now you just factor out the 6 from it. So if I take out the 6 that's in common, you'd have 6 times 7 to the K plus 1. No, sorry, not plus 1, plus n, right? Now, is that a multiple of 6? Yes. So 7 to the K plus 1 minus 1 was equal to all of these things. And it turned out to be a multiple of 6 because it's 6 times that amount, right? So therefore, the end of the proof is to just say therefore, 7K plus 1 minus 1 is divisible by 6. Is divisible by 6, and then you're done, so you can put a little box. So there's that. Okay, any questions about that? So I'm going to stick to similar questions like this on the test. I'll try to make the one with the recurrence relation even easier, So it was all perfectly easy until we got to those fractions at the end. I'll do my best to make it be something that's not fractions. The only problem is sometimes if you make something not have fractions, then it has really big numbers at the beginning. Because if you look back at that problem with the recurrence relation, do you see the numbers at the beginning were really small? If I had something that wasn't a fraction, like if I had bk equals 3 times 7 to the k plus 5 times 7 to the k, then I might have ended up with numbers at the beginning that were like 20 or 30. So there's always a consequence. If you have big numbers at the beginning, you might have small numbers at the end. But if you have small numbers at the beginning, you might have fractions at the end. So I'll do my best to make it easy in both ways. So that's all for today, and have a great fall break, and make sure you're ready for all these questions on the test on Monday. Actually, in fact, you know what? I might even have part of them maybe in class and maybe possibly part of them like take home or something like that. Because I don't think we should be able to, if you're really, really studying for it, you should be able to do these within 15 minutes. But I want you to be able to do it with a little bit less stressed out. So maybe I'll pick like 12 of them to do in class, and then maybe like 3 of them on the like take home maybe. Okay, so good job, everybody.